and then a 2 is the perimeters of the octagon, one with 8 sides, and so on. So in general, an going to be the length of the polygons with 2 to the n plus 1 sides. Okay. So the reason that we don't work with A3. So the reason Archimedes look at this is because, so for example, A8 is that he wants to find the length of the circles, and his reasoning is that when you take n very large, these polygons very close to the circles, so the length of this sequence an here gonna converge to the length of the circles. So of course back then he didn't prove anything about the conversion of the sequence, but he just computes this to approximate pi. So the question here for you is so of course if you want to quickly compute this, you need some form of formula that related this sequence an. So try to write this in terms of the previous term an. Okay, so find a formula for this, connecting these two guys. So once you have such a formula, you can quickly compute the next term and then see how the sequence behaves. So please try this. So if you finish, let me know. Okay, has anyone finished? Okay, so you just keep trying, right? So this is a good exercise. Okay, so if you have two positive numbers, so remember the mean value theorems. So I guess I can erase this part. So the mean value theorem says that for any function f, and if f is a nice differentiable, then this quotient is equal to f prime c for some c in between a and b. I think this from analysis 1. So if f is log, then f prime is 1 over x. So let's say z. So that is so you get exactly this. So the mean value theorem says that there is such a z. It doesn't tell you what exactly z is. You just give you what the existence of such z. But we only use the fact that z is between a and b, because then you can conclude that 1 over z is bigger than 1 over b. Is this clear now, or you still don't understand this part? Okay. And then you apply these inequalities with b equal to 1 plus 1 of x, and a is 1. Log 1 is 0, so you can throw this away, and then you multiply both sides with 1 over x, and you get exactly the inequality that we want. Any questions? Okay, let's if instead you look at this function. Now instead of power x, you have power x plus 1. So it's a little bit bigger than f, because you can see that g is f times this factor, which is getting very small when x is large. Right? So 1 plus 1 of x. So you increase this a little bit. Then this function, and you can show that you can try to follow all this proof to show that g is now decreasing. So therefore this sequence is a decreasing sequence. So if you replace n by n plus 1, then you get a decreasing sequence. And now you can combine these two facts to show that that the sequence, the limit of n exists, because yeah, so I will leave this as exercise for you to show this, that this one is a decreasing function, you try to follow the same proof as this one here. Now this follow that, oops, sorry. This follow that you know, before we have established that the sequence AN is increasing. Now you need an upper bound to show that the limit exists, right? But an upper bound is very easy if you know that this sequence here is decreasing, because you know that AN is always less than BN, right? As I mentioned, BN is this times this, and this factor is bigger than 1, and this is exactly AN. So in fact we have AN is smaller than BN. But because Bn is decreasing, this is less than Bn minus 1 and all the way to B1. And you can compute B1, which is 4. So the sequence An increasing and has an upper bound 4, so the limit exists. And in fact, I think this is the original definition of the number E. E is defined to be the limit of this sequence. Okay, so let me show you another way to prove that the sequence AN is increasing. No, it's very simple and it doesn't use any derivative at all. And so what we use is a fact that for any k and any positive number x1, xk positive, so k here is a natural number. Then we have the average of xk is always bigger than the geometric average. So you maybe I write it in this way. You take the product. So here you take the sum and you divide by k to have the average. And on the right hand side, you take the product, and this is kind of average. You take the k root of this product. And this is always true. And this is something called the AMGM inequality. So this stands for arithmetic mean, and this is geometric mean. And the inequality that we, I think you already see many times, is k equal to 2. And you get this way. And now since xk are positive, you can write x1 as a square and x2 is b square. And this is nothing but this inequality. So let me show you how to prove that the AN increasing from this inequality, right? So if you go back to our definitions, and you can think of this as the product of n number equal to, so this is n numbers, right? And so let me rewrite this in a different way so that we can apply it quicker. So let's raise everything to power k. Then this inequality becomes this. So these are equivalent way of writing AMGM inequality. So you have n numbers here. So let's take in a number 1 as well. Then you have n plus 1 number, and you're gonna apply this inequality for k equal to n plus 1, and here is x1, and here xn, and then xn plus 1. So this is gonna be less than or equal to the sum of these two guys. And then you divide by the number of terms, and you raise to that power. But the top here is equal to, you have n numbers, right? And you have this 1 here, and you do the calculation, then this is exactly n plus 2. So this is n plus 2 over n plus 1, so that is exactly 1 plus 1 over n plus 1 raised to the power n plus 1, but this is exactly n plus 1. So we have shown that an is less than an plus 1 using just this AMGM inequalities. Is this clear? Do you have any questions? Any questions? Okay. Okay, let's continue with series and where is this? Okay. Okay, so series You can think of a series as an infinite sums of a sequence. So given a sequence an, we're gonna try to define its sums. And the way we define the sum is very similar to the way we define improper integrals. I think type 2, I think. Remember when we have an infinite integral like this, we're gonna replace this by some finite numbers and calculate that finite integral and then take the limit as this go to infinity. So we're gonna try to do the same things to define a series, because now this is it has infinite sum and you cannot take the sum of infinite things because it just takes a lot of time. So we truncate this at certain level n, and we call the sum that we obtain, so the sum I from 1 to n, to be the n partial sum of the series. So Sn goes from, is the sum of an plus a1 plus a2 plus an. And so just in case that this happen in the future, if you have a sequence just start at 3, for example. So remember, a sequence can start at any index. Then we still call this the n partial sum. So the n is the index that the series, the partial sum stop. It's not the number of terms in the series. So for this sequence here, the partial sum start with 3, and so it's plus an. So then we do this, the same. The last step is the same as when we define the improper integrals. Now we have a sequence Sn that depend on this index n. Then you try to figure out if the limit when n go to infinity of this Sn exists. And if it exists, then we define this to be these infinite sums. So that is our definition. So we define this if the sequence of the partial sums converge to S, then we define the series, the sum from 1 to infinity of an to be equal to S, and S is called the sum of the series, sometimes the value of the series. And so all that was said can be summarized by this formula. And this is also the limit of Sn. And in the case the limit doesn't exist, we say that the series diverges. So let me give you a couple of examples. Yes, why don't you try this? And then we have more example later on. So try to evaluate this series. So now the index is you. So let's try to compute this series by compute the partial sum. So let's now let's take Sn. Then you change this from 1 to n. So try to find a formula for this partial sum Sn. Okay. When you finish, let me know. So have you finished? Anyone found a formula for Sn? You must. That is a formula for one of the terms, and then you do have to add them up. So this is similar to remember when you do partial fraction, when you compute integrals, we saw that this one can always be split. Yes, that's very good. N over n plus 1. This you can always split this this fraction as long as the degree of the top is less than the degree of the bottom. You can always split into these terms when the constant you have to figure out. And then if you do that, you see that in this case, if you have 1 here, it's exactly equal to this. And now you can apply this formula. Now instead of x, you have j. So let me write down here. So Sn is the sum j from 1 to n, 1 over j minus 1 over j plus 1. And if you cannot work this out quickly, you can write down all the terms and see this way you see all the cancellations and so on. And the last two terms gonna be when j equal to n minus 1, you get this. And when j equal to n, you get this. Now there's a lot of cancellation going on because you get these two cancel and this guy cancel and so on. And this one gonna be cancelled with the one after that, and this one also cancel with the one previous. So these two cancel, and the only thing left is this two, the first term and the last term here. So finally, what we get is Sn is 1 minus 1 over n plus 1, or you can write this as n over n plus 1. Now, by definition, this series is equal to the limit of Sn, if that limit exists. So we compute the limit. So the limit of Sn is certainly 1, right? Because this one goes to 0. So this series is 1. Any questions? The next exercise is more difficult in that you have to show that the Sn diverge, so it doesn't, the sequence partial sum does not have a limit at all. And so the hint for you is, so try to show that in this case Sn actually can get arbitrarily large, and it's actually go to plus infinity as n goes to infinity. Anyone finished? maybe I will show you how to do this. And this is not difficult, but if you haven't seen this before, so what is Sn? So Sn is the sum of the first n terms, right? And this is certainly bigger than what? So this is the smallest among them, right? Among all these n terms. So the sum gonna be smaller if you replace every term by this smallest one. And then you have exactly n terms. And this is square root of n. And certainly square root of n goes to infinity. And Sn is even bigger than that, so certainly Sn also goes to infinity. Is this clear? Okay, let's do one more example, which is, so let me, this will be simple and you should be able to do this. So let's say you look at an, which is equal to minus 1 to the n. So so our series now gonna be like this. So find the formula for the partial sum Sn. Okay? And you finished? Let's see. Yes, it's diversion, and you can find the formula for Sn quite easily because so the term is like this. You start with n equal to 1, so it's minus 1, 1, minus 1. So you can see that as n gonna be equal to -1 if n is odd. So if n is 1, 3, 5, 7, and so on. Whereas if n is even, then you have an equal number -1 and 1. For example, as for you take sum of just 4 terms, so you get 0. So the sequence of Sn is -1, 0, -1, 0. And certainly we've seen earlier that this cannot have a limit because the limit of the odd sequence and the even sequence are different. Okay, so let's see if there is anything else. Okay, so let's do another exercise to show that this sequence diverge. Let's say now you take 9/10. So this should be 1/2, right? Let's make it even smaller by raise this power, increase the power to 9/10. So prove that this one diverge. So have you finished? Well, if you compare with 1 over n, then you have to show that this one diverges. Right? Can you show that this series diverges? Okay, so we're gonna look at this later on. For now, so what I want is to imitate that's the proof before for this series here. So now our Sn is like 1 plus 1 over 2 to power 9 over 10, right? And all the way to 9 over 10. Then you do just like before. This one is bigger than n time, because it has n term, and times the smallest one. And this is still n to the power 1 over 10. And 1 over 10 is positive, so this gonna goes to infinity. This goes to infinity when n go to infinity. So in this case, we still have a divergent sequence, a divergent series. Is this clear? Okay. So by the same proof, using the same proof, actually you can replace this power here, which is a half here and 9 over 10 here. You can replace this by any p less than 1. So if p less than 1, then the series diverge, because now the proof goes through without any change. Well, there is some change, but it's not essential because here is p. Then still the smallest one is here, and you have n terms. So then you get n to the power 1 minus p. And as long as p is less than 1, then the series diverges. So to have a series of this form that is converse, you have to increase p enough so that the terms more enough, so when they sum up, you get something finite. And it turns out that this series is going to converge when p bigger than 1. Then it's converse. Now the case p equal to 1 is interesting because you cannot use this proof anymore. Let's look at the case p equal to 1. If you do this, then you get exactly 1 here. And it gives you nothing because if you know that this sequence is always bigger than constant, you cannot say anything, right? If you only know that Sn is bigger than 1, you can say nothing about Sn. It can diverge, it can converge, but in fact, you can still show that this one diverge to infinitive. So try to show that this one goes to infinity. So we cannot use the same proof as before, but you Anyone see how to do this? So note that Sn is an increasing sequence, right? Because every time you're increasing n by 1, you add one more terms into the sum. So positive term into the sum. So the sequence Sn is increasing. And so to show that it goes to infinity, you just need to show that it can get arbitrarily large. So what you can do is actually you imitate the proof that's fail. So before we, if we try this, it's gonna fail, right? Because it gives you just one. But now let's try this. So I guess it's easiest to do this. Let's look at the index 2n. Okay, so you sum all the way from 1 to 2n, and you can split this into two sums. And the next sum is okay. So this is nothing but the partial sum Sn, right? But this is the sum of the first n terms. And now for the next part, you imitate exactly what we have before. So you have n terms here, and the smallest one is 1 over 2n. So this is Sn plus a half. So we have shown that for this sequence, S2n, so every time you increase, you multiply the index by 2, you increase the sum by at least a half. right? So then certainly this can this partial sum can get arbitrarily large, because if you want to increase by 1, you can double it again. So in general, if you multiply the index with 2 to the k, then you have this. And so this can get arbitrarily large if you just let k goes to infinity. Is this clear? Do you have any questions? Any questions at all? Okay, so you see that by very elementary means, we don't even need something called the integral test or comparison test that we will learn later on. You can show that this series diverges when p less than 1. So let's conclude by finishing also by very easy means. So we have shown that this series diverge. Actually, it goes to infinity. If p less than or equal to 1. Now, let's consider the case p bigger than 1. So now there is some hope that this series may converge, because when you increase p, the terms getting smaller and smaller, and you hope that eventually you would get something converge, and that is actually the case. And converge if p is bigger than 1. So remember that this series is defined by the limit of this partial sum, and as I mentioned earlier, this in our case all the terms are positive, and every time you increase this n by 1, you add in one more term. So the sequence of the partial sum in our case is an increasing sequence. An increasing sequence. What is this now? Sorry, this is J. P. So Sn is increasing. So if you want to show that this one converges, all you need to do is to, by the monotone conversion theorem, you need to show that this one is bounded above, right? So try this. Try to show that this one is bounded above. Anyone finished? So let me show you how to do this, because the idea is very simple. It was just a simple comparison, just like before when we showed that for this range the series diverge. Now see, when you want to show that Sn is bounded, because of this it suffices to show that when n equal to 2k, this one S as the index 2 for k is bounded. And when you do that, simply because if you know that say S2, S4, and S8, S16, and so on, a bounded sequence, and for any n you can find, if Sn here, you can find something of this form that's bigger than n, and then Sn is say less than S32, and then bounded by some constant. So you need to show that this one is bounded by n. You have to find this for all k. And the idea is just like before. So you write down this sequence, this partial sums. P. Yes. And then so you will see why we do this. So we're gonna group like this. And you see the idea. So the next group gonna be 31p and so on. So get this out of the way. And the idea is that for each of these, you can estimate very simply, because now you get this is going to be less than, you have two terms here, and the biggest one is the first one. So instead of picking the smallest one like before when you're proving diversion, you pick this, the biggest one to get this inequality goes the other way. And here you get four terms, and the biggest one is 1 over 4p, and similarly you get 8 over 8 over p, so on, 16, so this follows that Sn is always less than the sum of this series. Let's say j equal to 0 to infinity 1 over 2 to the power j times p minus 1. Because you can cancel one of these power and you get p minus 1 down here, right? And then this number is just 2 to the j. You start with 1 here, 2, 4. So you get this series. And now you see why we need p, because on 1, because you want this to be positive, right? If p is less than 1, then this one negative, so in fact this is something that's very large. And so now all you have to do is to show that this series converges. And that would give you the number n. And in fact, this is something called the geometric series. So if you let R to be 1/2 to the p minus 1, this one is going to be belong to 0, 1. Then the series that I have here is simply R to power j. Maybe I should write here. So you take R to be and in fact we will see, maybe we do this next time. This series converges. This is something called the geometric series, and the value of this series, as long as R is less than 1, which is in our case here, is exactly equal to 1/1 minus R. So we have shown that Sn is always less than this number here, where R is 1/2 to the power p minus 1. So that's shown that the series, this series converges. So we will prove this next time. And, so this is something called the P series. And we have shown today that when P is less than or equal to 1, the P series diverges. P bigger than 1, then the series converge.